Now imagine that our monitor could display 6 characters, meaning it has 2 character rows, and in each character row we could show 3 characters. And imagine that as an example, the characters that we want to show are A, B, and A in the first character row and A in the second character row. So obviously you would expect in our RAM to write 0x41 as the ASCII code for the A, for this first A, then 0x42 for the B, the ASCII code for B, 0x41 for the next A, then 0x41 again for this one, 0x41, and finally 0x41 for the last one. But one thing that I wanted to mention is that you might expect that the way that the display would scan the lines would be that it first would scan the first scan line of the first character, then it would go for the second scan line of the first character, and so on. In fact, this isn't the case. This isn't the way that the display scans the pixels. Instead, it first scans the first scan line completely. So it would be the first scan line of all the characters in the first character row. And we explained about the abstractions, character rows, and scan lines in the previous lectures. Then it would go for the second scan line and would scan that, and it would go on until completely scans all the scan lines. Now later I would explain based on the different monitors that we have how many times the scanning would need to be done in a second and why that is. But for now, as I promised you before, that only listen to the abstractions that I define and unlearn everything that you know from the graphics card from before. So let's go to our graphic card and see how such thing would be done. But before that, I also wanted to mention some other things here. Let me actually wipe these things out so you could better see. So imagine that you would expect, obviously, the graphics card to first give the monitor the value of 30H. In hex, which is obviously 00110000, to scan the first scan line of the first character. Then you would expect it does it the value, it gives the monitor the value of FC. Why? Because this is 1. For now you ignore 1 pixel between different characters. So it would be 11111100, and this is FC in hex. And later, for the first scan line of the next character, you expect again the graphics card to give the value of 30H to the monitor once more. And then as the monitor would go to scan the second scan line, you would want the graphic card to start giving the monitor the mapping, the character mapping for the second scan line. Obviously, this would be 0111 and 100, which is 78 in hex, and we explained before. And for the B, this would be 0110, which is 6, and then 0110, which is again 6 again. So you would expect that the graphics card to first give the monitor the values of 30 in hex, FC, and 30 again, and then it gives it 78, 66, and 78 again, and it will go on until it scans all the scan lines. Now let's go in graphics card and see if the graphics card that right now we have could achieve that. So obviously our memory cell would need, or RAM would need to be 6 bytes long, right? Let me actually make this smaller, because our display is able to save or to show 6 characters, so you would need 1 memory cell for each character. Now later I will explain to you why in the graphics card, in the architecture of the first graphic card that we will see later, it's actually twice that. Means for 6 characters we need 12 memory cells. But for now, just imagine the minimum is 6 memory cells, and each character for each position on the display. So in the first position, we would expect the value of A to be shown, then B, then A again. The first character row would be completed, then A, and A again. Two other abstractions I need to define to you. And the first thing is that sometimes we call this memory as the refresh memory. We also might call it the display buffer. And this ROM, we might call it the character generator ROM, as it generates characters. And you already know that each character is mapped or is encoded using 8 bytes. These 8 bytes would be for the A, and these 8 bytes are for the B. The position of each character is specified in the RAM. But we have a problem. Let me introduce you the problem. You see, my goal was to first give you the problem so you would have an intuition, so that when you see those things on the graphic card, you wouldn't need to memorize these things. It would be intuitively in your mind. So you would expect that first the 41 to fall on the data bus of the RAM, which is connected to the address bus of the ROM. So you would expect to have 0x41 on the address bus of the ROM and to select the 78. I actually think I forgot to put another line in here, so we should have the first byte would actually be the value of 30 in hex. I think I wiped that out. So the first byte would be this one, and then the 41 0x41 would select the value 30H. Obviously 30H would go to the shift register, which is 0011 0000, and it would start give the bits one by one from this part to the on the video pin of the display, and display would put them depending on whether or not they are zeros or ones. We would add the background or the foreground color, and that's right for the first byte. But as you see, next, if we put the value of 42 on the data bus connected to the address bus of the ROM, if this address is 0x41, the next address here would be 0x42. So the next thing that is scanned is 78. While as we explained, we would expect FC right now to be given to the monitor. You see, we said that the monitor is scanning the first line. So you would expect after 30 in hex, you would give it the value of FC in hex, right? But right now we are giving it 78. So instead, the monitor would show this combination of pixels on the first row for the B, and that's wrong. We would expect the graphics card to give the value of FC to the monitor, so monitor would show this combination of characters, which eventually would lead to showing the B on the second position of our display. So this is the problem that we have, and let's see how we could address this problem. So let me again wipe these things out. So you would expect to put a counter in here which has 3 bits, and it would be 000 at the beginning. Now our ROM, the address bus of our ROM, wouldn't be only 8 bits long. It would instead be 11 bits long. Now see what happens. So first 41 would be put on the address bus of the ROM, which would be 0x41, and actually let me show it to you using the binary. So it would have 0100 as the 4, 0001 for the 1. Then this 3000 would also be added in here. So we would have, let me change my color, we would have 000. This address should be the address of the first memory cell. So 30x would be put on the shift register, and that would be selected. Next, 42 would fall on the address bus. Let me show it in here so you would better see it. So 42 would be 0100 0010, and 3 zeros would also be part of that. So we would have 000. This address is exactly 8 bytes more than this address. 8 bytes more than this would exactly be FC. So as you see right now, FC would be given to the shift register, and then it would be shifted and would be given to the monitor. What would happen next is that now 0x41 would be given on the address bus. And again, as nothing has changed, we would have the same value in here, and again 0h would be given to the shift register and monitor. You see, we would expect to have 0h, then FC, then 30, then FC, and then 30 again for the first scan line of all the characters. After this, what would happen is that now 000 would become 001. Now see what happens. So 0x41 would fall on the address bus again. I write it in here. We would have 01000001, and these 3 bits would be 001. So this address is exactly the address of 78, one address more than this value. Therefore, 78 would be given to the shift register, it would be shifted, would be given on the video pin, and therefore the display, so 78 would be given to the monitor as the first byte of the second scan line. And after that, what would happen is that now again we would have the value of 42 on the address bus, so it would have 01000010, and the 3 pins which are 001, we would have 001, and this address is exactly 8 bytes bigger than this address of 78, so which, if you count 8 bytes bigger than that, would be the value of 66. So now 66 would be given on the display and would go to the monitor, and this would completely go on until all the scan lines of the first characters would be scanned, and next it would move to the first scan line of the second character row. So as you see, we need more elements in our graphics card. It's not just a RAM, a shift register, and a ROM. We need some counters, and also, as I said, that it needs to go to the second character row, so you would need some other registers as well. We are feeling the need of having more counters and registers, and in fact we would have. So let me just zoom out to go to our graphics card in here. This is the architecture of the first graphic card. Let me actually make this bigger. So in our graphics card, and everything would be explained later, I just want to tell you that how they designed it, why they designed it. You see, this is so important to answer the question why. So in our graphics card, we have some RAMs, the refresh memory, which are these set of RAMs, a character generator ROM, which is this one, and also a shift register. These are the most important elements of our graphics card that you saw. We need all of them. But we would have a set of registers and counters. And you might say, well, we don't see that many registers, even though, well, right now you don't know what these elements are, but a lot of counters and registers are all packed in this chip. The name of this chip is 6845, which is the most important element in the monochrome display adapter or in the first graphic card. A lot of counters and registers we would have that we could program them. Why would we want to program them? So we could work with with different displays and different monitors. And I think by now you have an understanding how that would help us to have different counters. Just imagine if in our graphics card, instead of a counter of 3 bits, we would have a counter bigger, which could mean that either our characters has been mapped with, or character box is longer, or character is mapped with more bytes, or so on. Actually, right now you might be a bit confused about this. So sorry if it got too much confusing. You could watch it over and over again, or a couple of times, and also work out the logic. Write down the binary values and understand why the logic is that. Why do we need these 3 bits in here? So in the next lecture, I also would explain something more about this graphics card. And also don't forget that right now you have a huge amount of information about the graphics card. Don't think that, oh, it is a 1 hour thing. The important factor is that I spent a lot of hours over understanding these wires, and I put them one by one in here, so you would have an understanding by looking at all of it. So it means that a lot of data has been packed. It's not that 1 hour, it's a lot of hours packed inside 1 hour for you. So that's the purpose of any video course. That's the purpose of any book. That's why right now, before 10 years before, someone had to put 10,000 hours to be the best in something. Right now it might be cut by half, because there are many video courses and many books that have packed a lot of information in a short amount of time. So I see you in the next lecture.